4 astronauts just came home from the moon, and the last 13 minutes of their trip could have killed them all. Artemis II launched with a heat shield that NASA knew was broken. Over 100 cracks, chunks missing. A flaw with no backup, no escape, and no second chances. So they changed the flight path instead. And they flew anyway. We will look at what cracked, why they flew, what they cancelled mid-mission, and what a former astronaut compared to the disasters that came before. If you enjoy the channel, subscribe. We bring you the real story behind every mission. Now, prepare yourselves. We begin. December 2022, the Orion spacecraft named Artemis I splashed down in the Pacific Ocean after a 25-day loop around the moon. No crew aboard. A perfect test flight, NASA said. Cameras rolled. Engineers cheered. The whole world watched a capsule bob in the water like a cork, heat shield facing down, still smoking from re-entry. Then the divers got close. What they found on the underside of that capsule was not supposed to be there. Chunks of material had broken away, not worn away smoothly, the way the design intended, broken off. In over 100 separate locations across the surface of the heat shield, the protective outer layer had cracked, spalled, and ejected material into the atmosphere behind the spacecraft. The heat shield on Orion is made of a substance called avcoat. It looks almost like dark foam baked into a honeycomb structure. The entire point of avcoat is to burn away during re-entry in a slow, controlled fashion, carrying heat away from the capsule as it goes. Think of it like a candle melting at just the right rate, so the flame never reaches the table beneath. The material is engineered to sacrifice itself, to erode, to absorb thousands of degrees by turning itself into gas and carrying that energy away from the crew module. But on Artemis I, it did something else. It cracked, it popped, and pieces of it flew off. Engineers launched an investigation that would last more than a year. What they eventually found was a pressure problem buried inside the material itself. As the capsule screamed through the upper atmosphere, hot gases penetrated into the avcoat and became trapped inside pockets within the structure. The pressure built, and when the outer char layer cooled slightly during what is called the skip phase of re-entry, that trapped gas had nowhere to go, so it blew outward, like steam forcing the lid off a pot. The cracking did not destroy Artemis I. The spacecraft came home. The crew module temperatures stayed within design limits, and that fact would become the central argument NASA used when deciding what to do next. But here is what made this discovery genuinely alarming. The heat shield for Artemis II was already installed on the capsule by the time Artemis I landed. Already sealed, already integrated into the vehicle. NASA had not waited for the results of the first test flight before building the second spacecraft, because the schedule demanded both vehicles move forward in parallel. So when the inspection teams photographed those 100 cracks, there was no simple fix. The capsule sitting in the vehicle assembly building at Kennedy Space Center already wore the same flawed design on its belly. The investigation reports went to engineers, then to managers, then to an independent review team. A publicly released version of that review team's final report was handed to journalists and outside experts. Many of those experts immediately noticed that significant sections had been blacked out, redacted, removed from public view. Former NASA engineers who had spent careers studying heat shields read the document and said they could not evaluate the safety case because too much of the reasoning was hidden. And yet, the mission moved forward. What NASA found when they dug into the physics of that cracking would force them to make one of the most controversial decisions in American spaceflight since the 1980s. They could not replace the shield. They could not delay long enough to rebuild the capsule. So they asked a different question entirely. Could they change the way the spacecraft fell? The answer they arrived at was counterintuitive, and some engineers thought it was reckless, because the fix was to make re-entry hotter, not cooler. And that raises the question of what exactly happens to a spacecraft during those final minutes. Because what Orion was about to face during Artemis II was not just extreme heat, it was a specific sequence of forces that had to work in a precise order, with zero room for error and no way to help the crew if anything went wrong. Picture a meteor hitting the atmosphere. That bright streak of light you see on a clear night is not fire in the conventional sense. It is friction so violent that the air itself cannot get out of the way fast enough. The air compresses in front of the falling object and heats to temperatures far beyond what any metal can survive. The streak you see is the object burning, eroding, turning itself into light. Every spacecraft returning from deep space faces the same physics. The Orion capsule coming home from the moon carries so much speed that it arrives at the upper atmosphere, traveling at roughly 25,000 miles per hour. That is fast enough to cross the entire continental United States in under 7 minutes. At that speed, the air in front of the capsule cannot move out of the way. It piles up. It compresses so violently it becomes plasma, which is a fourth state of matter, a superheated gas so energetic that electrons strip away from their atoms. The plasma glows. It envelops the capsule in a sheath of fire that reaches temperatures close to 5,000 degrees Fahrenheit on the outer surface of the heat shield. 5,000 degrees is hotter than the surface of lava. It is hot enough to melt steel in seconds. It is roughly half the temperature of the visible surface of our star. The crew inside sits behind that shield. Between them and 5,000 degrees of plasma is roughly 16.5 feet of avcoat, insulation, and metal. A layer that has to work perfectly, every single time. The way avcoat is supposed to work is elegant. As the outer surface heats, the material begins to char. That char layer acts as an insulator, slowing the transfer of heat toward the crew module. But the critical part happens just beneath the char. The avcoat underneath sublimes, meaning it turns directly from solid to gas without becoming liquid. That gas has to escape outward through the char layer and carry thermal energy away with it as it goes. The heat literally flows out with the departing gas. When it works, it is beautiful engineering. The shield gets thinner and thinner as it sacrifices itself, and the crew stays cool. On Artemis I, something went wrong in that sublimation step. The gas tried to escape outward through the char layer and found itself trapped. The char had sealed over before the gas could vent. Pressure built up underneath. And when the capsule briefly rose back out of the thickest part of the atmosphere during the skip maneuver, the outer char cooled slightly. That cooled char became brittle, and the gas trapped beneath it had enough pressure to fracture it, to eject it. 100 locations, chunks of heat shield flying off behind the capsule at 20-some thousand miles per hour, burning up in the atmosphere. The crew module survived because the underlying structure is built with significant margin. Engineers knew some erosion, and even some unexpected behavior was possible. But 100 cracking locations was far beyond what any model had predicted. The gap between prediction and reality was wide enough to worry everyone who studied it. And here is where the decision became genuinely difficult. NASA's engineers determined they understood the cause: trapped gas, pressure buildup, char fracture. They believed that understanding. They built a fix around it. The fix was to stop the char layer from ever cooling enough to trap gas in the first place. To do that, you had to expose the shield to intense heat for a shorter but more consistent period. You had to hit the atmosphere steeper and faster, keeping temperatures elevated throughout, never giving the char a chance to cool and seal. The counterintuitive logic, more heat, applied more consistently, was safer than a gentler but interrupted approach. But that fix had never been tested on the actual hardware. The modified trajectory was built on computer models, ground tests, and the Artemis I data. Every engineer who felt confident in it was betting confidence in a model, not a result. One former NASA astronaut looked at that gap between model and result and wrote a letter, a public letter, addressed directly to the NASA administrator. And what he wrote in that letter reached back across decades of spaceflight history to a pattern he said he recognized. Charles Kamada is not a theorist. He flew to space aboard the Space Shuttle Discovery in 2005, the first mission after the Columbia disaster. He sat inside a vehicle while engineers on the ground debated whether foam damage to the wing had compromised his vehicle's heat protection. He knows what it feels like to return to Earth inside a capsule and wonder, in the minutes before re-entry, whether the shield beneath you is going to hold. So in January of 26, 3 months before Artemis II launched, Kamada sat down and wrote an open letter to NASA Administrator Jared Isaacman. He signed his name he published it publicly, and he said plainly that the agency should not fly. His argument was specific. He said NASA had not fully identified the root cause of the Avcode cracking. The pressure and trapped gas theory was plausible. He said, but the agency had not proven it conclusively. And building a modified re-entry trajectory on top of an incompletely understood failure mode was, in his words, like treating a symptom without diagnosing the disease. He wrote that history shows accidents occur when organizations convince themselves they understand problems they do not. That sentence was aimed at something much larger than Artemis. Anyone who has spent time studying American spaceflight disasters recognized exactly what Kamada was pointing at: the institutional patterns. The way technical concerns get translated into risk assessments. The way risk assessments become confidence. The way confidence becomes a launch decision. He was not alone. Dan Rasky, an advanced entry systems expert who spent more than 30 years working at NASA, described the situation publicly. He said flying with an incompletely understood failure mode was like standing at the edge of a cliff on a foggy day. You could not see how far the drop was. Jacqueline McCleary, a physicist who studies rare and catastrophic failure events, made a different and equally important point. One former astronaut had publicly estimated a roughly 1 in 20 chance of disaster during re-entry. McCleary said that number was not grounded in actual probability calculations. It was a gut feeling. Scientists do not actually know what the odds of failure were, she said, because the data needed to calculate those odds honestly did not exist. That is the part that deserves full attention. Not that the risk was 1 in 20 or 1 in 100, but that nobody could compute the actual number. The failure mode was real. The fix was untested on flight hardware, and the probability of catastrophe was genuinely unknown. NASA's leadership reviewed all of this. Administrator Isaacman met with engineers, outside experts, and the review team. In January 2006, he announced he supported proceeding. He said he had full confidence in the Orion heat shield. Some experts who had previously expressed concerns said the additional data addressed their questions. Others maintained their objections. The crew, for their part, said publicly that they trusted the plan. Commander Reed Wiseman, a naval aviator who had spent years evaluating risk for a living, said that if the crew stuck to the modified re-entry path, the heat shield would be safe to fly. He had studied the engineering data himself. He chose to go. Pilot Victor Glover acknowledged the risk directly. He said the heat shield and the parachutes were systems with zero fault tolerance, no redundancy, no backup. If they failed, the mission and everyone aboard were lost. And then 4 people strapped themselves into a capsule on April 1, 2026, and a rocket the height of a 32-story building lit its engines. What followed was 10 days of history, records broken, the lunar far side seen as no human had ever seen it, a moment of pure awe that the world shared. But underneath all of it, in every mission briefing, in every engineering console at Johnson Space Center, the heat shield question never went away. And on flight day 8, something happened that made controllers look very carefully at the vehicle's propulsion system. 6 days into the mission, Artemis II had already done something extraordinary. The 4 astronauts had swung around the far side of the moon on April 6th. They had traveled farther from Earth than any humans in history, surpassing even the Apollo 13 crew's record set 56 years earlier. They were roughly 248,000 miles from home. The images they sent back were stunning. Then, quietly, flight controllers on the ground noticed something in the telemetry from the European Service Module. A small helium leak. The European Service Module is the cylindrical section attached to the back of the Orion crew capsule. It provides propulsion, power, life support resources, and the engine burns that shape the spacecraft's trajectory. Helium is used inside the module's propulsion system as a pressurant, meaning it pushes fuel and oxidizer into the engines when burns are needed. A leak in that helium supply is not immediately catastrophic, but it is the kind of thing that demands attention. Flight controllers made a decision. On flight day 8, they cancelled a planned manual piloting demonstration. Commanders Wiseman and Glover were supposed to take direct manual control of the spacecraft and put it through a series of movements, testing the crew's ability to fly Orion by hand in deep space. It was one of the more publicly anticipated demonstrations of the mission. It did not happen. Instead, controllers used that time window to gather more data on the helium leak, running additional tests of the propulsion system to characterize exactly how much helium was escaping and how fast. That same day, a second planned activity was also cancelled, a demonstration of Orion's radiation shielding system, in which the crew would deploy a physical shielding structure to protect against solar radiation, was quietly removed from the schedule. The reason given was that the team needed to prepare the cabin for the demands of re-entry. Two separate demonstrations cut from the same flight day, one for propulsion concerns, one for entry preparation. A viewer watching the mission coverage might have missed both cancellations entirely. NASA confirmed the helium leak was small and did not affect mission safety. That statement is almost certainly accurate in the context of that specific mission. The leak was characterized, its behavior was understood in flight, and the vehicle performed as needed for the return home. The data collected will reportedly inform propulsion system modifications for future Artemis flights. But the wider picture is worth sitting with. A spacecraft flying 4 humans around the moon was found, mid-mission, to have a leaking pressurant system. 2 planned test objectives were removed from the schedule, partly as a result, and all of this happened in the shadow of a heat shield that the agency knew going in was not performing as designed. The mission was not designed to be a 10-day journey from the start. Early proposals for what would become Artemis II ranged from 8 days to 21 days, depending on what objectives were attached to it. The version that flew, the free return trajectory around the lunar far side and back, was always going to last approximately 10 days. There was no version of the mission that flew longer and then got cut short. The video title framing of "Came Home Early" points at something real, just not a last-minute decision to abort. It points at a mission shaped from the beginning by limitations, limited by a heat shield that could not handle the original skip re-entry, limited by a service module that could not enter lunar orbit under its own power, limited by a trajectory that had to be made steeper and faster to protect a flawed material. Every decision that shaped the final 10 days of that mission traced back to what inspectors found on the bottom of a capsule bobbing in the Pacific Ocean in December 2000, and the astronauts knew all of it. They flew anyway, which raises a question that goes deeper than engineering. On April 10, 2010-6, the Orion spacecraft named Integrity separated its service module at 7:33 in the evening Eastern Time. The cylindrical section that had carried them to the moon and back fell away, exposing the heat shield at the base of the crew capsule. From that moment forward, the 4 astronauts had no propulsion, no ability to adjust their path, no way to change what was coming. They were falling. 20 minutes later, at an altitude of 400,000 feet above Earth's surface, Integrity hit the upper atmosphere traveling at roughly 24,600 miles per hour. That is about 35 times the speed of sound. The plasma formed almost instantly. From outside the capsule, the vehicle would have looked like a fireball. A self-contained sun streaking across the upper sky, bright enough to be visible from the ground in the right conditions, trailing a wake of ionized gas that glowed in colors ranging from white to deep orange. From inside, the astronauts felt the deceleration begin. The spacecraft was engineered to keep forces on the crew below 4 times the normal pull of gravity, roughly 4 times the weight of their own bodies pressing them into their seats. That is significant, but survivable. Less than a fighter pilot pulling hard in a tight turn, but sustained for minutes rather than seconds. What the crew could not feel directly was what was happening to the shield beneath them. The avcoat was charring. The outer surface, exposed to 5,000 degrees of plasma, was burning away exactly as designed. The question, the one that had driven years of investigation and an open letter and redacted reports and cancelled tests, was whether it was burning away in the right way. The modified trajectory meant the capsule came in steeper and faster than Artemis I had. The skip phase, where the vehicle briefly dipped into the atmosphere and then rose again before making its final descent, was shortened to a shallow loft maneuver. The goal was to keep heat applied consistently, to prevent the outer char layer from cooling, sealing, and trapping gas beneath it. For 13 minutes, nobody knew if it was working. Jeff Radigan, NASA's Artemis II flight director, had described those 13 minutes at a briefing the day before. He said he kept a mental checklist running of every system that had to perform in sequence. The heat shield had to hold. The parachute system had to deploy at the right altitude. The capsule had to maintain the correct orientation throughout entry, because if it tumbled, the heat shield would no longer face the plasma, and the crew module would not survive. At 7:53 in the evening, the 6-minute communications blackout began. The plasma surrounding the capsule absorbed radio signals. No data came down from the spacecraft. No voice contact. Mission Control could see nothing, hear nothing, know nothing. The 4 astronauts were alone, in a fireball, cut off from Earth, trusting a material that had cracked over 100 times on its previous flight. 6 minutes of silence. Then signal returned. Orion was intact. The trajectory correction burns over the prior 2 days had held the capsule on its precise approach angle. The drogue parachutes deployed at 22,000 feet. The 3 main parachutes unfurled at 6,000 feet. Integrity hit the water at roughly 20 miles per hour off the coast of San Diego, within less than a mile of the target. Splashdown confirmed. The cheering at Johnson Space Center was immediate and enormous. 4 astronauts, alive. A mission completed. A record broken. The farthest humans had ever traveled from Earth, survived and home. But the celebration existed alongside a quieter, more unsettled question, because the real test of whether the heat shield had held was not visible from inside the capsule. The crew could not see the bottom of their own spacecraft, and the results of what happened to that shield during those 13 minutes would only become clear after divers photographed it in the water. That investigation was already underway before the crew even stepped out of Orion. Before the recovery helicopters had lifted the last astronaut out of the capsule, a team of divers was already in the water around Integrity. Their job was specific and time-sensitive. The heat shield on the underside of the capsule had just survived, or partially survived, a 5,000-degree plasma bath. The material that remained attached to the shield's surface would begin to interact with seawater almost immediately. Salt corrosion, pressure from recovery equipment, even the turbulence from helicopter rotors could all alter the physical evidence. NASA needed photographs of the shield in its post-re-entry condition before any of that happened. Aircraft had also been positioned near the splashdown zone to capture imagery of the capsule during descent, before it even hit the water. Both approaches aimed at the same goal: preserve the most accurate possible record of how the Avcoat had behaved during those 13 minutes. What NASA found, and the full results of that analysis, will take months to process. They're described publicly in the hours after splashdown. The capsule had followed what mission managers called a near-perfect flight path during re-entry. The trajectory was executed almost exactly as planned. That was the flight dynamics result. The heat shield result was separate, and NASA said explicitly that detailed inspection of the hardware would continue over the coming months. The careful language was itself informative. A mission that went perfectly in every way would have produced a simple, clean statement about shield performance. The measured tone of the post-splashdown comments suggested engineers were still looking carefully. The data from the flight, combined with the physical inspection of the returned hardware, would determine whether the modified re-entry profile had actually solved the cracking problem, or had simply managed it well enough that the mission succeeded. That distinction matters enormously. A managed risk that succeeded once is not a proven solution. It is a data point. The question engineers were now asking was whether the Avcoat on Artemis II had cracked in the same pattern as Artemis I, in a modified pattern, or barely at all. Because the answer directly shapes what comes next, Artemis III is more complex. The crew will need to dock Orion with a lunar lander in orbit, transfer between vehicles, descend to the lunar surface, ascend back up, and then return to Earth. Every one of those steps builds on hardware that is assumed to work, and the heat shield is required to work at the end of every single one of them. NASA Administrator Isaacman acknowledged, even before the Artemis II crew splashed down, that the approach taken for this mission was not the right long-term solution. He said the agency was fixing the Avcoat design for future capsules, specifically addressing the permeability of the material so that gas could escape outward without pressure building beneath the char layer. The redesigned heat shield is planned for Artemis III. Planned, not yet built, not yet tested, in the conditions that reveal whether a heat shield design actually works. The astronauts of Artemis II came home. That is real, and it matters, and it required extraordinary courage from 4 people who understood the risks completely and chose to fly anyway. But the engineering problem that sent divers swimming beneath a floating capsule to photograph cracks before the salt water could set in, that problem is still being solved. And Artemis III is scheduled to launch next year. Here is what most coverage of the Artemis II heat shield story missed. The cracking on Artemis I was described as unexpected. Engineers said their pre-flight models did not predict it. Over 100 locations showed char loss beyond what the computer simulations had anticipated. And that gap between what models said and what reality produced is the part that deserves the most attention. Avcoat is not a new material. It is the same class of heat protective compound that flew on the Apollo program in the 1960s and 70s. Engineers chose it for Orion specifically because of that legacy. Decades of flight data. Decades of understanding. A known material for an already difficult problem. But the Avcoat used on Orion is not identical to what flew on Apollo. The original formulation used asbestos, which is now banned. The modern version uses a different fiber chemistry, applied in a honeycomb tile structure, rather than the older spray-on method. Each cell of that honeycomb is filled with the Avcoat compound individually. The process is labor-intensive, precise, and introduces potential inconsistencies across the 16.5-foot diameter shield. The investigation after Artemis, I determined that those inconsistencies in the honeycomb filling allowed hot gases to penetrate into some cells more easily than others. In those cells, gas became trapped, pressure built, the char fractured. What the investigation could not fully determine, according to multiple outside experts, was how consistently the root cause had been identified across all the locations that cracked. Were all 100 locations cracking for exactly the same reason? Or were some locations failing through a slightly different mechanism, one that the modified re-entry trajectory might not fully address? This is the concern Kamada raised most sharply. If you design a fix for mechanism A, and 90% of the cracks were caused by mechanism A, your fix handles 90% of the problem. The remaining 10% still exists. And on a system with zero fault tolerance, the remaining 10% is the part that can kill you. NASA's engineers ran scenarios involving more extensive heat shield damage than expected, and concluded the underlying structure would remain intact. That conclusion gave the agency confidence to proceed. But the scenario analysis, the modeling, the ground tests, all of it was built on an understanding of the failure mode that outside experts said was still not complete. The modified re-entry trajectory worked on Artemis II in the sense that the crew came home alive. That is a meaningful result. It means the worst-case scenarios, the ones where the shield sheds so much material that the underlying structure is compromised, did not occur. The crew module survived. But whether the Avcoat performed better than Artemis I, worse, or about the same under the new trajectory, is still being evaluated. Those results will shape every engineering decision between now and when Artemis III sits on the launch pad. What is already confirmed is this: the heat shield design flying on Artemis III will be different. The Avcoat permeability will be changed to allow gas to escape more easily before pressure can build. That design change is an acknowledgement, written into the hardware itself, that the version flown on Artemis II was insufficient for long-term use. 4 people flew around the moon on a spacecraft the agency knew needed an upgrade it had not yet completed. That fact sits alongside every record they broke, every image they captured, every scientific observation they sent home. Both things are true at once. The mission was historic. The machine underneath it was flying with a known flaw and an untested fix, above a planet that could not reach up and help if anything went wrong. Charles Kamada flew to space on the mission that followed Columbia. He knows what it means to launch after a disaster. And he knows what it means to look at an organization and see the same patterns repeating. Columbia was lost in February 2003. During launch, a piece of foam insulation broke free from the external tank and struck the leading edge of the left wing. The foam had broken off on previous flights. Engineers had observed it, flagged it, studied it, and ultimately accepted it as a known risk because previous flights had landed safely despite the foam shedding. The problem became normalized. On Columbia's final mission, the foam strike created a hole in the wing's thermal protection system. During re-entry, superheated plasma entered through that hole. The vehicle broke apart. All 7 crew members were lost. The formal investigation that followed identified 2 causes: a physical cause, the foam strike, and the wing breach, and an organizational cause, the culture within NASA that had accepted a known, recurring problem as an acceptable risk because previous missions had survived it. The phrase the investigators used was normalization of deviance. When something goes wrong but does not result in catastrophe, there is a psychological tendency to reclassify the abnormal event as normal. The foam was always shedding. The flights were always surviving. So the foam became acceptable until it was not. Kamada's open letter in January 2222 did not use the phrase normalization of deviance, but the pattern he described was the same: a heat shield cracking in over 100 locations on an uncrewed flight. An investigation that partially explained the cracking, a decision to fly the next mission with the same hardware and a modified trajectory, a confidence built on data that outside experts said was incomplete. Every element of that sequence carries echoes of what the Columbia investigation described. NASA pushed back firmly. Associate Administrator Amit Kshatriya pointed to the Artemis I flight data, the ground testing, and the engineering models as a strong foundation for the decision to fly. He said the agency had high confidence in the system. Administrator Isaac Mann reviewed the analysis personally and said he supported the mission. And the crew, the 4 people whose lives depended on that judgment, trusted it. Wiseman, Glover, Coach, Hansen, all experienced, all fully briefed, all chose to climb into that capsule. There is a version of this story where NASA made the right call, where the modified trajectory solved the cracking problem well enough, where the engineering judgment was sound and the investigation was more complete than outside critics acknowledged, where Artemis II was a carefully managed risk that paid off. That version is possible. The crew is home. The data is still being analyzed. The final judgment on how the shield performed is not yet in. But there is another version of this story, one where the heat shield on Artemis II cracked in some of the same ways as Artemis I, where the fix reduced but did not eliminate the problem, and where 4 human beings came home, not because the engineering was perfect, but because the margins held. Kamada's letter ended with a line drawn from the history of the agency he spent his career serving. He wrote that history shows accidents occur when organizations convince themselves they understand problems they do not. That sentence did not stop the launch, but it is sitting in the public record, and the engineers pulling apart Integrity's heat shield right now know exactly what it means. There is a number attached to Artemis that does not appear in the mission briefings or the splashdown coverage. Through 2000 and 2005, the total cost of the Artemis program was estimated at roughly $90 billion. That is not a criticism hiding inside a fact. It is context, enormous context. When an organization has spent $90 billion building toward a single goal, the pressure to continue toward that goal is structural. It exists in budget justifications, in contractor relationships, in the political agreements between NASA and dozens of international partner agencies that have signed the Artemis Accords, in the careers of thousands of engineers, scientists, and administrators whose work depends on the program moving forward. That pressure does not make anyone dishonest. It does not mean the engineers who reviewed the heat shield data were lying when they said they were confident. But pressure of that magnitude reshapes how questions get asked and how uncertainty gets weighted. It makes the argument for proceeding easier to construct and the argument for delay harder to sustain. One engineer reportedly argued for delaying Artemis II by more than a year to replace the heat shield with a redesigned version. That argument lost. The counter-argument, that the modified trajectory could protect the crew adequately with the existing hardware, won. Both positions were held by serious people with serious credentials. The one that prevailed was also the one that kept the program on schedule. Scientific American raised this tension directly after splashdown. in a conversation about what Artemis II cost and what it returned. Critics pointed to the $23 million space toilet that broke mid-flight and required the crew to use manual backup systems multiple times during the mission. They pointed to the heat shield problem. They asked whether $90 billion spent on a program that puts humans around the moon without landing them was the right allocation of resources. Supporters pointed to what the program actually produced: a crewed vehicle that traveled farther from Earth than any humans in history. Real engineering data on deep space life support, navigation, and propulsion systems. The foundation for Artemis III, which aims to put boots on the lunar surface for the first time since 1972. A demonstration, visible to the entire planet, that humans can still reach beyond low Earth orbit. Both sets of arguments are serious, but what the $90 billion number reveals most clearly is that Artemis II did not exist in a world of pure engineering decisions. It existed at the intersection of engineering, politics, international commitments, budget cycles, and institutional momentum. The heat shield flew with a known flaw, partly because of physics. The physics of a capsule that was already built, already installed, already integrated into a vehicle that had a launch window and a crew and a global audience, and partly because of something harder to quantify: the weight of everything that had already been spent. Administrator Isaacman said plainly that the approach taken for Artemis II was not the right long-term solution. He also said he was fixing it. He also said the program would aim to launch at least one lunar mission per year going forward. That cadence, one mission per year, with a redesigned heat shield that has never flown on a crewed vehicle, is the context inside which Artemis III will be built and launched. The records broken by Artemis II were real. The courage of the 4 people who flew it was real. The organizational and financial pressures that shaped every decision around that flight were also real. And the heat shield investigation is still ongoing. 3 separate systems on Artemis II showed unexpected behavior during the mission. The heat shield issue was known before launch. The helium leak in the service module was discovered in flight. And the space toilet failed repeatedly during the 10-day journey, requiring the crew to use manual backup systems multiple times before engineers working remotely identified the root problem. NASA was careful in how it described the toilet failure. The agency specified that the problem was not with the toilet itself, but with the system responsible for dumping liquid waste overboard once a collection tank filled. That overboard dump system failed to operate correctly on multiple occasions. The crew adapted. The mission was not compromised. Taken individually, none of these 3 failures would define a mission. Every complex spacecraft accumulates anomalies during flight. The space shuttle routinely generated thousands of in-flight technical notes over its operational life. Systems that work perfectly in ground testing encounter conditions in space that ground testing cannot fully replicate. Anomalies are expected, but the 3 failures on Artemis II share a characteristic. Each one involves a system that had either never been tested in actual deep space conditions before, or had not been tested at a level sufficient to predict its behavior during this specific mission profile. Orion had never carried a crew beyond low Earth orbit before April 1st, 2006. Every system aboard the spacecraft was in some meaningful sense flying for the first time under the conditions it would actually face. The ground testing, the computer simulations, the Artemis I uncrewed flight data, all of it was preparation. None of it was the real thing. That is not a criticism of the engineers who built Orion. It is a description of what a test flight actually is. A test flight is the first time you find out what you did not know. The heat shield cracked on Artemis I because ground testing did not replicate the exact pressure dynamics of actual re-entry. The toilet failed on Artemis II because ground testing did not reproduce the exact operational demands of a 10-day deep space mission. The helium leak in the service module fits the same pattern. A small leak, discovered mid-mission, requiring real-time characterization by engineers on the ground, prompting the cancellation of planned test objectives to create time for additional data gathering. All of this is what test flights look like when they are working honestly. Anomalies surface. Data is gathered. The information shapes the next vehicle, the next design, the next mission. The discomfort lives in what the test results revealed about the gap between what was modeled and what actually happened. a heat shield that cracked in over 100 places on an uncrewed flight, a toilet that failed repeatedly on a crewed one, a helium pressurant leak that required real-time engineering response while the spacecraft was 250,000 miles from Earth. Each gap represents something engineers did not fully know going in, and Artemis II, the mission that will attempt an actual lunar landing with actual astronauts, will introduce new systems that have also never flown in the conditions they will face. A lunar lander, either a SpaceX Starship variant or a Blue Origin vehicle, will dock with Orion in lunar orbit. That docking procedure has never been performed. The lander will descend to the surface. That has not happened in more than 50 years. Each new system is another test. Each test reveals what the models missed. The real question that engineers are asking as they analyze Integrity's returned heat shield, is whether the gaps revealed by Artemis II are narrow enough to fly through on the next mission. April 6, 2026. The Orion spacecraft named Integrity swung around the far side of the moon. There are moments in spaceflight history so visually extreme that they require no embellishment. The crew of Apollo 8, in December 1968, became the first humans to leave low Earth orbit, the first to reach the moon, the first to see the far side. Their photograph of Earth rising above the barren lunar horizon became one of the most reproduced images in history. It changed how humans understood their own planet. The Artemis II crew did something Apollo 8 could not. They flew farther around the moon, on a trajectory that took them to roughly 7,500 kilometers beyond the lunar far side, and they carried cameras that Apollo 8 did not have. They observed from a vantage point no human eyes had reached in any earlier mission. At closest approach, the moon filled their windows like a basketball held at arm's length. The far side, the hemisphere that permanently faces away from Earth due to the synchronized rotation of the moon with its orbit, spread below them in detail no previous crew had seen directly. The far side is not the dark side. That is a common misconception. The far side receives sunlight in the same cycle as the near side. What makes it different is that it never faces Earth. It has a different geological character than the near side, more heavily cratered, with fewer of the large dark basalt plains called Maria, that give the near side its familiar face. The crust on the far side is thicker. The reasons for that asymmetry are not fully understood. As Integrity passed beyond the limb of the moon, the crew briefly lost radio contact with Earth. The lunar body itself blocked all signals. For a period of time, the 4 astronauts were unreachable, farther from Earth than any humans before them, on the far side of a world 250,000 miles away, in a capsule with a cracked heat shield, completely silent. Then they came back around. Signal returned. Mission controllers at Johnson Space Center heard their voices again. The crew spent that flyby making naked-eye observations of the lunar surface and collecting photographic data that scientists said would help determine what the moon is made of, at a level of detail previous missions could not provide from. Their trajectories. Voice notes recorded in the moment captured geological observations that will keep researchers occupied for years. They also, as planned, attempted to recreate the Earthrise photograph. The image of Earth cresting the lunar horizon, first captured by Apollo 8, was shot again from a perspective no Apollo crew could reach. The Artemis II version of Earthrise comes from farther out, from a position on the far side that places Earth in a geometry those earlier astronauts never achieved. The record they broke was confirmed on April 6 at 1:56 in the afternoon Eastern Time, 248,655 miles from Earth, farther than Apollo 13's crew had reached in 1970, when that vehicle swung around the moon on its own emergency-free return trajectory after an oxygen tank exploded. Apollo 13's record had stood for 56 years. It fell to Integrity on a Tuesday afternoon, and the 4 people who broke it were sitting inside a capsule with a heat shield that had cracked on its previous flight, orbiting a world with no rescue capability, watching Earth rise above the lunar horizon for the first time in half a century. 248,655 miles from Earth. Hold that number for a moment. The International Space Station orbits at roughly 250 miles above the surface. The distance Artemis II achieved was nearly 1,000 times farther than that. If you drove a car at highway speed without stopping, it would take you more than 400 years to cover the same distance. At that point in the mission, the 4 astronauts were beyond the reach of any rescue vehicle ever built. There is no spacecraft that could have launched, reached them, and brought them home in time to matter. The communication delay between Integrity and Earth was still small enough to allow real-time conversation, unlike the multi-minute delays of a Mars mission. But no one on Earth could do anything physically meaningful to help them. They were, in the most literal sense, on their own. The record is significant, not just as a number, but as a statement about what the human body can withstand in deep space. Every mission to that distance gathered medical data. The Avatar investigation aboard Artemis II used biological devices called organ-on-a-chip, miniaturized models of human tissue, to study the effects of deep space radiation and microgravity on human physiology. The data those devices collected will inform how future crews are protected on longer missions, including the eventual transit to Mars. The radiation environment beyond low Earth orbit is substantially different from what crews experience on the International Space Station. Earth's magnetic field extends a protective bubble around the planet that deflects much of the incoming cosmic radiation and charged particles from solar events. The International Space Station sits inside that bubble. The Moon does not. Artemis II crossed that boundary. The crew was exposed to the deep space radiation environment for the duration of their 10-day mission. Dosimeters aboard the spacecraft tracked exactly what they received. That data, combined with the organ-on-a-chip results, will help engineers design the radiation protection systems for the vehicles that go farther and stay longer. Christina Koch, one of the mission specialists aboard Integrity, brought particular significance to this part of the mission. She had already set the record for the longest continuous spaceflight by a woman, spending 328 days aboard the International Space Station. Her body's responses to deep space radiation, compared to her well-documented International Space Station radiation data, will give researchers a rare longitudinal view of how extended spaceflight affects a single individual across very different radiation environments. Jeremy Hansen, the Canadian Space Agency astronaut who rounded out the crew, became the first Canadian to travel to lunar space. He was also, at the time of the mission, one of the least experienced astronauts ever to reach the Moon's vicinity, having never flown to space before Artemis II. His medical baseline data, clean and unaffected by previous long-duration spaceflight, gives scientists a comparison point against his more experienced crewmates. 4 people, 4 different physiological profiles, 10 days in an environment that no human being had reached since 1972. The distance record was the visible milestone. The biological data is the invisible one. And the invisible data is what makes Mars possible. But while all of that was happening in the science racks and dosimeter logs, the mission was also approaching the moment that had worried engineers for years: the return. Jeff Radigan had been working toward April 10, 2206 for years. As Artemis II's lead flight director, he had spent that time building the plan for re-entry, running simulations, studying the heat shield investigation results, working through the modified trajectory with his team. He had held the numbers in his head so long, they had become something close to intuition. And then, on the day before splashdown, he stood at a media briefing and described what the next 24 hours held. 13 minutes, he said. 13 minutes of things that had to go right. He was not being dramatic. He was being precise. From the moment Integrity hit the upper atmosphere to the moment the main parachutes opened, the sequence of events that had to occur in correct order, at the right time, at the right angle, left almost no margin for deviation. The entry angle was the most critical variable. Orion had to arrive at the atmosphere on a path narrow enough that the capsule neither bounced off the atmosphere like a stone skipping off still water at too shallow an angle, nor plunged so steeply that the deceleration forces overwhelmed the heat shield and the crew. The corridor of safe entry angles is physically narrow. Coming in a fraction of a degree too shallow meant the capsule could skip out into a higher orbit with no fuel left to correct. Coming in too steep meant higher forces and more heat for longer. For the modified trajectory NASA was flying on Artemis II, hitting that corridor correctly was even more important than it would have been for a standard re-entry. The entire fix for the heat shield depended on the approach angle being maintained precisely. too shallow, and the skip extended. The char layer cooled. The trapped gas problem that cracked Artemis I could recur. Too steep, and other structural limits were challenged. Radigan put it simply at that briefing. They had to hit the angle correctly, he said. Otherwise, they were not going to have a successful re-entry. Let us not beat around the bush, he added. Those were his exact words. Mission controllers had spent the previous day and a half executing trajectory correction burns to keep integrity precisely aligned. 1 9-second burn on flight day 9. 1 8-second burn on flight day 10, the last firing of the service module before it was jettisoned. Each burn was calculated to keep the approach corridor within tolerance. At 7:33 in the evening on April 10th, the service module separated. At 7:37, Orion fired its crew module thrusters for an 18-second raise burn, adjusting orientation to align the heat shield for atmospheric interface. At 7:53, the capsule reached 400,000 feet and entered the communications blackout. 6 minutes, no data, no voice contact, nothing from the spacecraft. And then signal returned. The drogue parachutes deployed at 22,000 feet at 8:03. The 3 main parachutes opened at 6,000 feet at 8:04. The capsule splashed down at 8:07, within less than a mile of its target, off the coast of San Diego. 13 minutes, executed almost perfectly. The flight director, who had spent years building that plan, exhaled. And then, almost immediately, the questions that the mission had been designed to answer shifted from the realm of theory into the realm of data, because the heat shield was now at the bottom of a capsule floating in the Pacific Ocean, and the truth of what had happened to it during those 13 minutes was about to be examined in detail. 6 minutes of silence. That 6-minute window is worth dwelling on, because it is not just a communications inconvenience. It is one of the most physically extreme environments a human being has ever entered. As Orion hit the upper atmosphere at 35 times the speed of sound, the compression of air in front of the capsule created a plasma sheath. Plasma is not simply hot gas. It is gas in which electrons have been stripped away from atoms by the energy of the collision, creating a soup of charged particles that interacts with electromagnetic radiation in ways ordinary matter does not. Radio waves cannot penetrate plasma of sufficient density. The frequencies used to communicate with Orion were absorbed. Mission controllers sent signals. The signals hit the plasma sheath and stopped. No data came through. No voice. No telemetry. For 6 minutes, the 4 astronauts experienced something that almost no human has faced. They were in a vehicle undergoing the most violent phase of its flight, surrounded by fire hotter than the surface of lava, pressing into their seats under forces approaching 4 times their body weight, unable to communicate with anyone, with the knowledge that if the shield beneath them failed, there was nothing that could be done. They had prepared for this. Training covers the blackout extensively. Astronauts know it is coming, know its duration, know that silence from the ground is expected and normal during this phase. They monitor their own instruments. They keep their hands near the controls they cannot use during this automated phase of flight. They wait, but preparation and experience do not make the physics smaller. The plasma layer surrounding integrity was several inches thick at peak heating. The temperatures at the outer surface of the shield reached close to 5,000 degrees Fahrenheit. The crew module interior, separated from that plasma by the avcoat and the vehicle structure, stayed within survivable temperature ranges. Within the plasma itself, the ionized gas glowed in colors that shift from deep red through orange to white as temperatures increase. The capsule would have appeared from the outside as a self-illuminated fireball moving across the upper atmosphere, decelerating from hypersonic speed with each passing second, trailing a glowing wake. From inside, the astronauts saw none of that. The capsule's windows were oriented away from the plasma during entry, and the view was blocked by the vehicle's orientation. What they experienced directly were the forces, the sound, and the readings on their instruments. The sound during peak heating is described by veterans of previous re-entry profiles as significant. Structural vibration, acoustic energy from the plasma interaction with the outer surface. A vehicle that has been floating silently in space for 10 days suddenly becomes loud and physical. Then the plasma thins. The deceleration eases. The instruments begin showing expected values. The blackout ends, signal, voice, contact. Mission Control heard them. The room at Johnson Space Center, quiet during the 6-minute silence, heard the crew's voices come back through the communications loop. Integrity was intact. After the blackout, Orion still had approximately 14 minutes to reach the water. The parachute sequence that fills those 14 minutes is its own engineering story. The Orion capsule weighs roughly 19,000 pounds at splashdown. After fuel has been burned and the service module has separated, bringing something that heavy from hypersonic speed to a safe water impact requires a carefully staged deceleration system. At around 22,000 feet altitude, Orion ejected its forward bay cover, a protective cap over the parachute compartment. 2 smaller stabilizing parachutes called drogues deployed immediately. Their job is not to slow the capsule, but to stabilize it, keeping the capsule oriented correctly as it descends through the lower atmosphere and preventing it from spinning. At roughly 6,000 feet, the drogues pulled out the 3 main parachutes. Each main chute spans about 116 feet across when fully open. 3 of them together, deployed simultaneously, create a parachute canopy wider than a commercial airplane's wingspan. The deceleration from those 3 parachutes brought integrity from several hundred miles per hour to approximately 20 miles per hour at water impact. That final impact speed is not gentle. It feels like a significant jolt to the crew inside, but it is survivable. The capsule is designed to absorb that landing force through its structure and through the crew seats, which are engineered to cushion the deceleration. Victor Glover, the mission pilot, had specific responsibility for monitoring the parachute deployment sequence. As the drogue chutes opened and the main chutes followed, Glover confirmed each stage of the deployment with Mission Control as communications had been restored. There is a reason the parachutes receive attention alongside the heat shield in discussions of Artemis II risk. Glover himself said before the mission that the parachutes, like the heat shield, were systems with zero fault tolerance. If the parachutes failed to deploy correctly, the capsule would hit the water at a speed that no survival system could compensate for. The parachutes on Orion are similar in design to those used on Apollo, with decades of development layered on top. They performed correctly on Artemis I. They performed correctly on Artemis II. But Glover's statement before the mission was important for what it revealed about the category of risk facing the crew. Both the heat shield and the parachutes are single-point failure systems. There is no backup heat shield. There is no backup parachute system that deploys if the primary fails. These are the 2 systems that stand between the crew and death during the final phase of the mission, and each of them has to work the first time, every time. The Artemis program is aiming for 1 mission per year. Each of those missions will bring a crew home through the same sequence, the same plasma bath, the same 13 minutes, the same parachute deployment. Every flight, those zero fault tolerance systems have to perform. The Artemis II crew splashed down safely at 8:07 in the evening Eastern Time, within a mile of the target point southwest of San Diego. Recovery helicopters were already in position. Divers reached the capsule before the parachutes had fully settled. The crew was lifted out. They were healthy. They had been to the moon and back. And engineers were already turning the question forward. What does the shield look like? And what does that tell us about what we need to do differently before we try this again? The post-splashdown investigation into the Artemis II heat shield is structured in phases, and the full results will take months. The immediate phase, the underwater photography by divers, and the aerial imagery captured during descent, was designed to document the shield's condition before recovery operations disturbed the surface. Salt water, physical contact from recovery equipment, and time all degrade the quality of the forensic evidence. Speed was essential. The second phase involves bringing the Orion crew module back to Kennedy Space Center in Florida, where engineers will perform a detailed physical inspection of every square inch of the avcoat surface. They will photograph, document, and catalog every area of char loss, every crack, every location where material has ejected. That catalog will be compared directly to the Artemis I post-flight inspection record. The critical comparison is whether the modified trajectory reduced the severity and extent of cracking relative to Artemis I. If the avcoat performed significantly better, that is evidence that the modified approach worked. If the cracking is similar or worse, the conclusion is more complicated. NASA, Acting Associate Administrator Laurie Glaze, said after splashdown that the flight path executed during re-entry was near perfect. That is a flight dynamics result. It means the trajectory was achieved as planned. It does not yet tell you whether achieving that trajectory as planned produced the heat shield behavior that was hoped for. The distinction is important. The modified trajectory was designed to prevent the specific failure mechanism identified after Artemis I. If the trajectory was executed perfectly, and the shield still cracked in similar patterns, that would raise the possibility that the failure mechanism is not fully understood, which is exactly what Kamada's open letter warned about. If the trajectory was executed perfectly, and the shield performed substantially better, it suggests the fix was sound, and the engineering judgment that allowed the mission to fly was correct. The engineers examining that hardware in Florida know they are reading one of the most consequential engineering documents in current American spaceflight. What those cracks say, how many, how deep, in what pattern, will shape the design changes already planned for Artemis III's heat shield, and will inform whether those changes are being approached with complete information or partial information. Administrator Isaacman said before the mission that the approach taken for Artemis II was not the right long-term solution, and that NASA was fixing it. That statement acknowledged the flaw openly. It also committed the agency to a path forward. The redesigned AVCOAT formulation for Artemis III addresses the permeability problem. The material will be modified to allow gases to escape outward more easily, preventing the pressure buildup that causes the char to fracture. The new formulation has been tested in ground facilities. It has not been tested in actual deep space re-entry conditions. That test will happen when Artemis III's crew module comes home from lunar orbit, with the mission's 4 astronauts inside. Artemis II was not designed to land on the moon. It was designed to prove that humans could reach lunar space, survive it, and come home. It proved that. 4 astronauts returned healthy from a 10-day mission that covered nearly 700,000 miles. They gathered biological data that no previous deep space crew could provide, at the level of detail current technology allows. They observed and photographed the lunar surface from angles and distances no Apollo crew reached. They tested life support, propulsion, navigation, manual control, and communication systems in the actual environment those systems have to survive. And they revealed 3 anomalies: a broken heat shield behavior, a failing toilet dump system, and a helium leak that will directly improve the vehicles that come after them. That is what a test flight is for. The data from Artemis II flows into every decision being made right now about Artemis III, where the heat shield's AVCOAT formula changes, where the toilet system's overboard dump mechanism gets redesigned, where the service module's helium management gets modified. Each fix carries the fingerprint of what integrity found in space. Commander Reed Wiseman said after splashdown that no one on Earth would ever fully know what the 4 of them went through. He was right in a personal sense. But in an engineering sense, what they went through is being extracted from every instrument, every dosimeter, every biological chip, every camera, every pressure sensor, and every line of telemetry data that Integrity generated over 10 days. That extraction is the real mission. The images of Earth from beyond the moon, the record-breaking distance, the lunar far side photographs, those are the visible outputs. The invisible outputs are the engineering corrections that those 4 people purchased by flying a spacecraft that was not yet fully understood. The road to Mars runs through what Artemis learned: the radiation data from beyond Earth's magnetic field, the physiological responses of a diverse crew across 10 days of deep space exposure, the behavior of life support systems in an environment that ground tests cannot completely replicate, the performance of a heat shield under modified re-entry conditions. All of it matters. All of it is being analyzed right now. Artemis III is scheduled to attempt the first crewed lunar landing since Apollo 17 in 1972. A lander will descend to the surface. Humans will walk on the moon again, and the Orion capsule that brings them home will wear a heat shield built from what the divers are photographing underwater off the coast of San Diego. 4 people went to the edge of what humanity has reached. They broke a 56-year-old record. They flew with a known flaw, on a precise and untested fix, and they came home. What they left behind, in the data and the hardware and the honest accounting of what broke and why, is the foundation that the next crew will stand on. April 6th, 2210, 1:56 in the afternoon, Eastern Time. At that exact moment, 4 humans became the farthest from Earth any human being had ever been. The number confirmed by NASA was 248,655 miles. That is the distance the Orion spacecraft, named Integrity, reached as it swung around the far side of the Moon on a free return trajectory, pulled by lunar gravity and released back toward Earth. The previous record had stood for 56 years, set by the crew of Apollo 13 in April 1970, when an oxygen tank explosion forced that vehicle onto an emergency loop around the Moon and back. Apollo 13's record was born from catastrophe. Artemis II's was planned. To understand what that distance means physically, consider this. The International Space Station orbits Earth at roughly 250 miles above the surface. The Artemis II crew traveled nearly 1,000 times farther than that. If you stacked commercial airliners nose to tail to cover the same distance, the line would wrap around Earth nearly 10 times. At that point in the mission, no rescue was possible. No vehicle ever built could have launched, reached them, and returned them to Earth in time to matter if something had gone catastrophically wrong. The communication delay between Integrity and Mission Control was still small enough for real-time conversation. A few seconds at most, but that was the only connection. Words, nothing else. Commander Reed Wiseman looked out the window at Earth from that distance and described it in the mission's final press conference. He said the planet looked small enough to hold in his hands, that the feeling was not terror, but something closer to reverence. Mission specialist Christina Koch, looking at that same view, became the first woman to travel to lunar space, the first woman to break the distance record, the first woman to see Earth from beyond the Moon. Mission specialist Jeremy Hansen became the first Canadian to reach lunar space, the first person from his country to see the far side of the Moon with his own eyes. Pilot Victor Glover became the first African American to travel to lunar space. He had spent 341 days aboard the International Space Station before this flight. He knew deep space was different. He described the view of Earth from the far side as the kind of thing that changes how you think about the planet permanently. 4 people, 4 firsts, 1 record broken after more than half a century. But the record is also a data point in a larger story about what it costs to break it. These 4 astronauts reached that distance inside a vehicle, with a cracked heat shield, a leaking helium pressurant, and a toilet system that required manual backup procedures multiple times during the mission. They got there and back because the margins held and because the people flying and supporting the mission were extraordinary. The question engineers are now answering, as they photograph and catalog the returned heat shield, is whether those margins were wide enough to be reliable, or whether Artemis II was a success in the way that Apollo 13 was technically a success. A crew that made it home from a vehicle that was not supposed to work that way. There is a persistent and understandable confusion about the far side of the Moon that is worth clearing up before going further. The far side is not the dark side. That description is a misconception that has been carried forward for decades. The far side receives sunlight in exactly the same cycle as the near side. Every lunar month, both hemispheres experience roughly 2 weeks of daylight and 2 weeks of darkness. The far side is dark for half of every month, just like the near side. It is not permanently dark. What makes the far side different is that it never faces Earth. The Moon's rotation is synchronized with its orbit in a relationship called tidal locking, meaning the Moon completes exactly 1 rotation on its axis for every orbit it completes around Earth. The result is that one hemisphere, the near side, always points toward us, and the other hemisphere, the far side, always points away. No human being had ever seen the far side with their own eyes, until the crew of Apollo 8 passed around the lunar limb in December 1968. But Apollo 8's trajectory kept them relatively close to the lunar surface, and their view was limited by their position and the technology available. The Artemis II crew flew farther around and farther beyond the lunar limb than any Apollo crew had. Their trajectory took them approximately 7,500 kilometers past the far side, at an altitude and angle that gave them a view no previous crewed mission had achieved. What they described seeing was a surface fundamentally different from the near side. The near side has large dark plains called maria, ancient lava flows that filled giant impact basins billions of years ago and give the moon its familiar face. The far side has almost none. Its surface is more uniformly cratered, older in appearance, rougher. The crust on the far side is measurably thicker than on the near side, a difference that scientists have known from orbital measurements, but whose cause remains an active area of research. The crew spent their flyby making naked-eye observations of the surface, recording voice notes, and capturing photographs that scientists said would contribute to understanding the composition and geological history of the far side at a level of detail previous uncrewed orbiters could not provide from their positions. They also passed through a period of complete radio silence with Earth. The lunar body blocked all signals. For those minutes, the 4 astronauts were unreachable, farther from Earth than any humans before them, on the far side of another world, in a capsule flying on an untested fix for a known flaw, with no way to communicate with anyone. Then they came back around the limb. Signal returned. Mission controllers heard their voices. And what those astronauts brought back, in photographs, in voice notes, in biological data and radiation measurements, is now being processed by scientists who will spend years working through it. The far side of the moon was always there. It took this long and this much risk to get 4 human sets of eyes close enough to see it properly. There is a detail from Artemis II that received less attention than the heat shield and the distance record, but which tells its own story about what it means to test a spacecraft in the environment it actually has to operate in. The space toilet broke. To be precise, the toilet itself functioned. The failure was in the system responsible for dumping liquid waste overboard once a collection container reached capacity. On a spacecraft in deep space, waste cannot simply be stored indefinitely. It has to be processed and expelled. The overboard dump system failed to operate correctly multiple times during the mission. The crew adapted using manual backup procedures to manage the situation. The mission was not compromised. NASA was careful to specify that the problem was not with the toilet hardware itself, but with the dump system. That distinction matters for engineering purposes. But from the crew's perspective, the distinction was largely academic. They were 250,000 miles from any repair facility, managing a broken system with manual workarounds for 10 days. The cost of developing and flying that toilet system was reported at approximately $23 million. That number became a focal point for critics who questioned whether the Artemis program's expenditures were proportionate to its returns. Supporters pointed out that developing reliable waste management for deep space missions is genuinely difficult and genuinely necessary. A system that fails on a 10-day mission to the moon presents a manageable problem. The same system failing on a multi-month Mars transit presents a serious one. The toilet failure is worth understanding in the context of everything else that went unexpectedly on Artemis II. The heat shield cracking on Artemis I was not predicted by pre-flight models. The helium leak in the service module was not predicted. The toilet dump system failure was not predicted. Each one represents a gap between what engineers expected the hardware to do and what it actually did when exposed to the conditions of real flight. Ground testing cannot fully replicate space. That is a known limitation of the design process, and it is why test flights exist. But 3 separate unexpected system behaviors on a single 10-day mission is a data point about how much remained unknown when integrity left the launch pad. Every one of those failures will improve the next vehicle. The redesigned AVCOAT addresses the pressure buildup problem. The helium management system will be modified. The waste overboard dump system will be fixed. Artemis III will be a better spacecraft than Artemis II, partly because Artemis II broke in those specific ways. That is the honest accounting of what test flights cost and what they purchase. But it also raises the question of what happens when the test flight carries people, and the thing that breaks is not the toilet. Of all the hazards facing the Artemis II crew, the one that received the least public attention during the mission was also the one with the longest-lasting consequences: radiation. Earth's magnetic field extends a protective region called the magnetosphere around the planet. Inside that region, charged particles from the solar wind and cosmic rays are deflected away before they can reach the surface or the spacecraft in low Earth orbit. The International Space Station sits inside the magnetosphere. Its crew receives elevated radiation compared to people on the ground, but the magnetic field provides meaningful shielding. The Moon does not sit inside the magnetosphere. The Artemis II crew, from the moment they left low Earth orbit, was exposed to the full deep space radiation environment. Cosmic rays arriving from outside the solar system, charged particles from the solar wind, the potential for solar energetic particle events, sudden bursts of high-energy radiation from solar activity that can deliver significant doses in a short time. Over 10 days, the dose accumulated is not immediately life-threatening, but every particle interaction with human tissue carries a small probability of cellular damage. Some of that damage repairs itself, some does not. The cumulative effect of deep space radiation exposure over many missions, or over longer single missions, is one of the primary medical concerns for any program aimed at reaching Mars. The Artemis II crew carried dosimeters that tracked their radiation exposure in real time throughout the mission. They also carried the Avatar Investigation, a set of organ-on-a-chip devices, miniaturized biological systems that model how human tissue responds to radiation and microgravity simultaneously. Those devices were exposed to the same deep space environment as the crew, and the cellular responses they recorded will give researchers data on tissue-level radiation effects that cannot be replicated in any ground facility. Christina Koch's participation added a dimension that no previous lunar mission could provide. Her 328 days aboard the International Space Station generated one of the most detailed long-duration spaceflight physiological datasets ever collected for a female astronaut. Comparing her deep space radiation exposure data from Artemis II with her International Space Station baseline will help researchers understand how radiation environments at different distances from Earth affect the same individual differently. Jeremy Hansen's clean physiological baseline, never previously flown in space, provides a comparison against the more experienced crewmates. Wiseman's extensive station experience adds another data point. Glover, who had spent nearly a year on the station before this flight, bridges the two environments, 4 different radiation histories, 4 different physiological responses, 10 days of data from a region of space humans had not occupied in 50 years. That data is now with researchers, and it will shape the radiation protection systems, mission duration limits, and medical protocols for every deep space crew that flies after this one. Among the experiences the Artemis II crew described after returning home, one stands out as something that no training simulation, no briefing document, and no previous mission could have prepared them for. From their position in lunar space, the crew witnessed a solar eclipse. A solar eclipse, as seen from near the Moon, is fundamentally different from one seen from Earth. From Earth's surface, a solar eclipse occurs when the Moon passes between Earth and our star, blocking its light and casting a shadow on a narrow strip of the planet's surface. The event lasts minutes, and the shadow races across the landscape at over 1,000 miles per hour. From near the Moon, looking back toward Earth, the geometry reverses. Earth passes between the crew and the light source. What the astronauts saw was Earth as a dark disk surrounded by a ring of light, the entire atmosphere of our planet illuminated from behind, glowing in a halo of refracted sunlight. Every sunset and sunrise on Earth, happening simultaneously, visible as a single luminous ring around a world in shadow. Mission specialist Jeremy Hansen described the sight as producing audible reactions from the crew. A moment of completely unscripted awe from 4 people who had trained for years, specifically not to be surprised by anything they encountered in space. The scientific value of the observation extended beyond the emotional response. The crew recorded the event photographically and with voice notes. The precise appearance of Earth's atmospheric ring during the eclipse carries information about the composition and density of the atmosphere at different altitudes. Researchers studying atmospheric science and exoplanet detection, specifically the search for signs of life on worlds around other stars, can use images of Earth's atmospheric ring during such events as a calibration reference for what a living planet looks like from space. The eclipse was not a planned objective of the mission. It was a consequence of geometry. The crew happened to be in the right place at the right time, and they had the cameras and the awareness to document it fully. It is the kind of thing that only happens when you go far enough to see the geometry change. And it is the kind of thing that no unmanned mission captures with the same quality as human eyes and human voices describing what they see in real time. The crew came home with images and recordings of that moment. Researchers will study them for years, and the 4 astronauts who watched Earth go dark from 250,000 miles away will carry that image for the rest of their lives. One of the less discussed scientific contributions of the Artemis II mission involves a question that sounds simple but remains genuinely open. What is the moon made of? The broad outlines are known. The moon's surface is covered in a layer of fragmented rock and dust called regolith. The near side has large basaltic plains, ancient lava flows that formed when the young moon was geologically active. The crust is mostly anorthosite, a pale crystalline rock that formed as lighter minerals floated to the surface of a global magma ocean early in the moon's history. The interior has a small iron core, a mantle, and a crust that varies significantly in thickness between the near and far sides. But the details of that composition, particularly on the far side, remain poorly understood. The far side's thick crust, its near-total absence of maria, and its different surface chemistry compared to the near side, present a puzzle that orbital measurements alone have not resolved. The leading theories involve asymmetric cooling of the early moon, possibly influenced by Earth's gravity during a period when both bodies were much closer together, or a second smaller moon that collided with the far side billions of years ago and spread its material across that hemisphere. The Artemis II crew observed the far side surface during their flyby at a resolution and from an angle that no previous crewed mission had achieved. They recorded what they saw with high-resolution cameras and with voice notes describing features, colors, and surface textures in real time. That kind of immediate human observation, describing what the eye perceives in the moment rather than what a processed satellite image shows after the fact, carries scientific information that researchers have found genuinely useful from previous missions. Their images and observations will help geologists build a more detailed compositional map of the far side, contributing to the ongoing investigation of why the two hemispheres are so different. That question matters beyond lunar science. The moon formed from material ejected by a giant impact with the early Earth. Understanding what the moon is made of helps constrain what Earth's interior looked like 4.5 billion years ago. The crew also observed micrometeorite impacts on the lunar surface during their flyby, tiny flashes of light as small space rocks struck the surface at high velocity, events that NASA scientists described with visible excitement in mission coverage. Those impact observations are directly relevant to understanding the current rate of meteorite bombardment in cislunar space, which matters for designing habitats, equipment, and spacesuits for long-duration lunar surface operations. 4 sets of human eyes in the right place at the right time saw things orbital cameras cannot capture in the same way. That is one of the arguments for sending people rather than robots, and Artemis II made that argument with its data. The Artemis program has a price attached to it that defies easy comparison. Through 2025, the program had spent roughly $90 billion. That number encompasses the development of the Space Launch System rocket, the Orion spacecraft, the ground systems at Kennedy Space Center, the European Service Module, developed by the European Space Agency, years of integration and testing, and the operational costs of running one of the most complex engineering programs in human history. For context, the Large Hadron Collider, the particle physics instrument buried beneath the French-Swiss border, and the largest scientific machine ever built, cost approximately $10 billion. The Artemis program has spent 9 times that, across a broader set of international partners, over a longer timeline. Scientific American raised the tension openly. After Artemis II's splashdown, critics questioned whether $90 billion directed toward a program that in its current state sends 4 humans around the moon without landing them represented the right allocation of public resources. Supporters argued that Artemis is not just about the moon, it is about building the infrastructure for sustained human presence beyond Earth, with Mars as the eventual destination. The moon is practice. The systems, the medicine, the navigation, the life support, the communication architecture, all of it feeds the longer goal. Both arguments carry real weight. The Space Launch System rocket is the most powerful operational rocket in the world. capable of lifting more mass to orbit than any other existing vehicle. It was also criticized heavily for its cost per launch, estimated at over $2 billion per flight, compared to the rapidly declining costs of commercial alternatives. SpaceX's Starship, still in development during Artemis II, aims for a fraction of that cost per launch and carries more payload. Administrator Isaac Mann, himself a commercial spaceflight veteran who has flown on SpaceX vehicles, was explicit about the tension. He said the agency had taken on too many obligations and too many distractions. He described a need for urgency. He also set a goal of at least one lunar mission per year going forward, an ambitious cadence that would require resolving the heat shield problem, finalizing the lunar lander, and sustaining political and budgetary support across administrations. The cost question is inseparable from the risk question. $90 billion spent creates institutional pressure to continue spending. That pressure shapes how risk decisions are made. The engineer who argued for a year-long delay to replace the heat shield was also arguing to absorb delay costs, contractor schedule impacts, and political exposure at a moment when the program's critics were already vocal. The decision to fly with a modified trajectory instead was cheaper, faster, and, as it turned out, survivable. Whether it was the right decision will be answered partly by what the heat shield inspection reveals, and partly by whether Artemis III launches on schedule with a redesigned shield that performs as its engineers predict. Artemis II went around the moon. Artemis III has to land on it. The difference in complexity between those two objectives is not incremental. It is categorical. The Artemis II crew flew Orion on a free return trajectory, a path shaped entirely by gravity, requiring only small engine burns to adjust the route. They never entered lunar orbit. They never had to dock with another vehicle in space. They never transferred between spacecraft. They flew around the moon and came home. Artemis III requires Orion to enter lunar orbit, to rendezvous and dock with a lunar lander in that orbit, to transfer 4 crew members from Orion into the lander, to descend from orbit to the lunar surface in that lander, to operate on the surface for up to a week, to launch back from the surface in the lander's ascent stage, to rendezvous again with Orion in orbit, to transfer back, and then to perform the same heat shield-dependent re-entry that already pushed Artemis II's engineering to its limits. Each one of those steps has specific technical requirements that have never been demonstrated together in the actual operational environment. The lunar lander for Artemis III is currently expected to be a variant of SpaceX's Starship vehicle, a completely different spacecraft design from anything that has previously attempted a crewed lunar landing. Starship is enormous compared to the Apollo lunar module. It has never carried crew to the lunar surface. The procedures for transferring crew between Orion and Starship in lunar orbit, conducting a docking and a spacewalk in that environment, have not been demonstrated in flight. Blue Origin is developing a competing lander design called Blue Moon for later Artemis missions. Neither vehicle had completed crewed lunar orbit operations by the time Artemis II splashed down. The heat shield that Artemis III's crew will rely on for their return to Earth will be a redesigned version of the AVCOAT system. The new formulation addresses the gas permeability problem identified after Artemis I, but it will not have flown on a crewed deep space re-entry before Artemis III uses it. Artemis III will be the first flight test of the redesigned shield, just as Artemis II was the first flight test of the modified trajectory. Every new element introduced on Artemis III is another system that will find out in flight what ground testing missed. The crew of Apollo 13 became the record holders for the farthest human distance from Earth in April 1970. Not because anyone planned it, but because an oxygen tank in the service module exploded 2 days into the mission, and the lunar landing had to be aborted. Commander James Lovell, Command Module Pilot Jack Swigert, and Lunar Module Pilot Fred Hayes swung around the moon on a free return trajectory, using the limited resources of the lunar module as a lifeboat, and returned to Earth in a condition that nobody on the ground or in the spacecraft fully understood until the crew module splashed down safely. The mission is remembered as a successful failure. The crew survived. The engineering improvisation that kept them alive is genuinely remarkable. But the lesson Apollo 13 taught was not that improvisation under pressure produces good outcomes. The lesson was that a known vulnerability in the oxygen tank design had been flagged years before the mission and not adequately addressed. The tank had been damaged during ground testing, and the damage had not been properly assessed before the flight. The organization knew there was a concern and proceeded anyway. Artemis II's Orion heat shield problem carries a structural similarity to that history, a known issue identified on a previous flight, an investigation that partially explained the problem, a decision to proceed with the mission using a workaround rather than a redesigned component. Apollo 13 survived its workaround through extraordinary effort and significant luck. The margins that allowed the crew to come home were real but not comfortable. James Lovell, who broke the previous distance record that the Artemis II crew surpassed, recorded a message for the Artemis II astronauts shortly before his death in August 2010-05. The message was played to the crew during their mission. He had spent more than 50 years watching the record he set stand unbroken, set during a mission that almost killed him, and he lived to see it fall to a new crew flying an equally imperfect vehicle toward an equally ambitious goal. That continuity, from Apollo 13's desperate free return loop to Artemis II's planned one, from a crippled spacecraft limping home to a flawed one flying deliberately, carries something important about how human spaceflight actually works. It is never the clean story the press conferences describe. It is always people flying machines that are not quite ready, trusting margins that are never quite comfortable, pushing forward because standing still is its own form of failure. When Integrity splashed down on April 10, 2026, the 4 astronauts inside had been living in a volume roughly equivalent to a large walk-in closet for 10 days. 4 people, a space that size, moving between the crew module and the service module, exercising on a flywheel system that supported aerobic and resistive workouts, eating from a menu of 189 items that included barbecue beef brisket, macaroni and cheese, tortillas, nuts, and cookies, sleeping in shifts on a schedule built around the timing of their launch, managing a broken toilet, tracking a helium leak, studying the moon. When they emerged from the capsule into the Pacific Ocean recovery zone and were lifted by helicopter to the USS John P. Murtha, they were physically changed by what they had experienced. The transition back to gravity after 10 days of weightlessness is not comfortable. Blood pressure drops. The cardiovascular system, which in weightlessness no longer has to work against gravity to move blood toward the head, has to recalibrate. Astronauts returning from extended spaceflight often feel dizzy, disoriented, and physically weak in the first hours and days back on Earth. The Artemis II crew wore orthostatic intolerance garments during re-entry, compression suits designed to help maintain blood pressure and circulation during the return to gravity. They had exercised throughout the mission specifically to limit the physical deconditioning that comes with weightlessness. The medical evaluations aboard the recovery ship were the first assessment of how well those preparations had worked. In the days after their return, each of the 4 astronauts spoke publicly about what the mission had meant to them. Wiseman described it as the most special thing that would ever happen in his life, and said the 4 of them were bonded in a way that no one who had not been there could fully understand. Glover talked about the permanence of the change in how he saw Earth. Koch described the view of the planet from beyond the moon as something that altered how she understood her relationship to it. Hansen gathered his crewmates beside him at the post-mission press conference and told the audience that when they looked at the 4 astronauts, they were looking at a mirror. That what the crew had done was possible because of everyone who had built toward it. He asked them to look a little deeper and see themselves in what they were watching. 4 people went to the edge of what any human had reached. They came back changed. And what they said when they came back was not primarily about the distance or the record or the heat shield. It was about the planet they had left behind, seen from far enough away to understand its smallness and its singularity. The most important outputs of the Artemis II mission are not yet available to anyone. The heat shield inspection is ongoing. Months of detailed analysis will be required before engineers fully understand how the AVCoat performed during re-entry and whether the modified trajectory achieved what it was designed to achieve. That analysis will determine whether the redesigned shield planned for Artemis III is addressing the right problems completely or partially. The biological data from the Avatar organ-on-a-chip investigation is in the hands of researchers who will spend years processing it. The cellular responses of miniaturized human tissue models to 10 days of deep space radiation and microgravity will contribute to understanding how long-duration spaceflight affects human physiology at the molecular level. That information feeds directly into the medical protocols and radiation exposure limits that will govern how long astronauts can safely spend in deep space environments on future missions. The radiation dosimetry data from the 4 crew members is being analyzed alongside the organ-on-a-chip results. The comparison of doses received at lunar distance versus doses accumulated during International Space Station missions will refine the radiation risk models used to assess the health implications of missions that go farther and last longer. The photographic and observational data from the lunar flyby is being processed by planetary scientists. High-resolution images of the far side surface, recordings of micrometeorite impacts, geological observations made by trained crew members in real time. All of it is being catalogued and studied. That process will produce scientific papers, compositional maps, and refined models of the Moon's geological history over the next several years. The propulsion data from the helium leak investigation is informing the modifications planned for the European service module on future Artemis vehicles. The exact behavior of a slow helium leak in deep space conditions, characterized in real flight by the Artemis II team, gives engineers data that no ground test can replicate. The toilet failure investigation is producing a redesigned overboard dump system. Every anomaly, every measurement, every observation, every creak in the structure, and every pixel of imagery from 32 cameras, all of it is data. And all of it is still being turned into the knowledge that will make the next mission more capable and more survivable than this one. Artemis II completed its mission, but the mission's work is not finished. It is only beginning. It is worth pausing on who these 4 people actually were, because the composition of the Artemis II crew was itself a statement about where human spaceflight. Reed Wiseman, the commander, is a naval aviator and test pilot who has spent time on the International Space Station and has managed risk in high-stakes environments for his entire professional life. The choice to make him commander reflected NASA's need for someone who could make calm, immediate decisions when systems behaved unexpectedly. He did that throughout the mission. Victor Glover, the pilot, became the first African-American to travel to the Moon's vicinity. He had spent nearly a year aboard the International Space Station on a previous mission and brought that experience to a spacecraft he had never flown in the deep space environment. He was the person most publicly identified with, acknowledging the heat shield risk before the mission. He understood it and flew anyway. Christina Koch, mission specialist and the first woman to reach lunar space, holds the record for the longest continuous spaceflight by a woman. She brought more physiological data from extended spaceflight than almost anyone alive. Her presence on this mission was not symbolic. It was scientifically significant. The data she generated in deep space will be compared to her station baseline for years. Jeremy Hansen, the Canadian Space Agency mission specialist, had never been to space before April 1, 2006. His first spaceflight was to the Moon. His clean physiological and radiation baseline, uncontaminated by previous spaceflight exposure, is exactly what researchers studying deep space health effects need. He became the first non-American to travel to lunar space. Together, they represented something different from the Apollo era, when all 12 humans who walked on the Moon were American men who had come from military test pilot programs. The Artemis crew was diverse in background, nationality, experience level, and gender in ways that the program's architect said were deliberate. The scientific value of that diversity is real. The physiological data from a crew with varied profiles, varied prior exposures, and varied biological baselines is more informative than data from a crew that looks and has lived the same way. Space medicine advances faster when the dataset is broader. And beyond the science, there is something important about who humanity chooses to send to the edge of what it can reach. Those choices say something about who we think belongs in that frontier. The question that engineers are not publicly discussing in explicit detail, but that sits underneath every conversation about the Artemis III heat shield redesign, is what the failure mode actually looks like. On Artemis I, the shield cracked, but did not fail catastrophically. The crew module survived. The temperatures inside stayed within limits. A cracked, spalling shield that loses material is not immediately fatal if the underlying structure remains protected and the damage stays within the bounds the vehicle can tolerate. But there is a threshold beyond which shield damage becomes catastrophic. NASA's engineering models define that threshold, and the scenarios run during the Artemis II mission assessment showed the team believed the vehicle would survive even under conditions worse than expected. Those scenarios provided confidence that significant safety margin existed. The concern is not about the average case. The concern, the one that drove Kamada's letter and the outside experts' objections, is about the tail of the distribution, the scenario where the failure mechanism is not fully understood and therefore not fully bounded, where the model's confidence interval does not capture the real range of possible outcomes because the input assumptions are incomplete. If the redesigned AVCoat for Artemis III performs as its engineers intend, the permeability changes will allow gas to escape before pressure builds, the char layer will not fracture, and the shield will erode smoothly as designed. That is the expected outcome, based on the current understanding of the failure mechanism and the ground test results for the new formulation. If the redesigned AVCoat encounters a failure mode, the redesign did not address, either because the original failure mechanism was not completely characterized, or because the new formulation introduces its own unexpected behavior. The Artemis III crew will face re-entry with a shield performing outside its designed parameters, without a backup, without an escape system available during that phase of flight. With 13 minutes between the start of atmospheric interface and the moment parachutes can help. This is not a prediction that Artemis III will fail. The engineering work being done right now is serious, rigorous, and conducted by people who understand what is at stake. The redesign is informed by the most detailed understanding of the AVCoat failure mechanism that has ever existed. It is a description of what the risk landscape looks like honestly. An honest risk description is the only foundation on which responsible decisions can be made. Every piece of information recovered from the Artemis II mission feeds forward. The heat shield data feeds into the Artemis III redesign. The biological data feeds into Mars mission medical protocols. The radiation dosimetry feeds into exposure limits for longer missions. The propulsion anomaly data feeds into service module modifications. The toilet failure feeds into a redesigned waste management system. The manual control demonstration that was cancelled due to the helium leak will be rescheduled and completed on a future mission. The radiation shielding deployment demonstration that was also cancelled will be retried. Nothing that was learned is wasted. That is how test programs work when they function correctly. The broader Artemis architecture, the one that Isaacman described as a relay race toward a permanent lunar presence, and eventually Mars, depends on each mission building usable knowledge for the next. Artemis II built more knowledge than any mission since the Apollo program. It also revealed more gaps than optimists had expected. That combination, knowledge gained and gaps revealed, is exactly what the mission was designed to produce. A perfect mission with no anomalies would have been less valuable scientifically than a mission that found the edges of what the systems could handle. The heat shield cracking on Artemis, I found an edge nobody knew was there. The modified trajectory on Artemis II tested whether the fix worked. The redesign for Artemis III applies the answer. That is 3 missions worth of learning compressed into a knowledge chain that, if it holds, produces a reliable heat shield for every subsequent crewed mission to deep space. That chain is also the argument for the cost, not just the cost of Artemis, but the cost of doing this carefully rather than quickly. Each failure found in a test and corrected before a loss of crew event is in a real but unquantifiable way worth the investment it required to find it. The alternative, moving faster, cutting testing, accepting larger known unknowns in exchange for schedule, is not theoretical. The history of spaceflight contains the results of that approach. Columbia, Challenger, failures that came from accepting known problems, because the pressure to proceed outweighed the discomfort of delay. The engineers examining Integrity's heat shield in Florida right now are holding that history in their hands. Artemis II was watched by more people than any crewed spaceflight in decades. The mission launched on April 1, 2026, from Kennedy Space Center in Florida, and the footage of 4 astronauts riding the most powerful operational rocket in the world into orbit was broadcast across streaming platforms on 4 continents, simultaneously. The lunar flyby on April 6th drew viewing numbers that NASA described as the largest for any crewed space event since the Apollo era. The splashdown coverage on April 10th ran on multiple major streaming services simultaneously. A generation of people who grew up after the space shuttle era, who had never seen humans travel beyond low Earth orbit in their lifetimes, watched 4 people go to the moon and come back. That audience matters for reasons beyond the obvious. The Artemis program's long-term survival depends on sustained public and political support across multiple administrations, budget cycles, and international agreements. The science and the engineering justify the program's existence on their own terms, but public attention is the medium through which political will is transmitted into budget allocations. When the Artemis II crew broke the distance record, when the images of Earth from beyond the moon reached screens around the world, when 4 astronauts described looking at our planet from 250,000 miles away and feeling something shift in how they understood it, those moments created the kind of shared experience that transcends the technical details. The heat shield problem, the helium leak, the broken toilet, the redacted safety review, the open letter from a former astronaut warning of catastrophe. All of that was real, and all of it matters. It is the honest picture of what the mission cost and what it risked. And the images of Earth from the lunar far side are also real. The distance record is real. Christina Koch, seeing the planet she had orbited for nearly a year from a distance it had never been seen from by a woman before, is real. Jeremy Hansen's first ever spaceflight ending with him looking out a window at the far side of the moon is real. Both the risk and the achievement exist together. Both are part of what it means to push to the edge of what any human has reached. The next generation watching will have to decide what they believe about that trade-off. Whether the risk is worth it, whether the investment is justified, whether the frontier is worth maintaining. That question belongs to them. 4 people came home from the moon. The capsule that carried them is now being taken apart. In Florida, the heat shield inspection will take months. The biological data will take years. The scientific publications generated by the Artemis II mission will accumulate over the next decade. Some of what was learned will be incorporated into hardware before the year is out. Some of it will reshape how we think about deep space medicine in ways that are not yet foreseeable. Artemis III is scheduled to launch in 2027. If it launches on schedule, it will carry 4 astronauts into lunar orbit, dock with a lander that has never carried crew to the surface, and attempt the first human lunar landing in more than 50 years. The astronauts selected for that mission will walk on the moon. They will do it wearing a heat shield, redesigned from the lessons integrity taught. Beyond Artemis III, the architecture calls for regular lunar missions, a gateway space station in lunar orbit, a permanent surface habitat, and eventually a sustained human presence on another world for the first time in history. Each of those steps is farther than the last. Each requires hardware that has not yet been tested in the environment it will face. Each will produce anomalies that ground testing did not predict. That is not a reason to stop. It is a description of what the frontier actually is, an edge beyond which the models are incomplete and the knowledge gaps are real, and the only way to close them is to go. The people who built and flew Artemis II knew all of this. The engineers who examined the cracked heat shield on Artemis I and built the best fix they could with the hardware they had. They knew. The flight director who memorized the 13-minute checklist and held his breath through 6 minutes of plasma blackout. He knew. The 4 astronauts who strapped in on April 1st, with full awareness of every system that was not quite ready, they knew. They went anyway, because the cost of not going compounds over time. Every decade that humans stay in low Earth orbit is a decade of knowledge not gathered, of systems not tested, of margins not measured, of gaps not found before they become catastrophes. Artemis II found some of those gaps, and the crews that come after will fly safer because of what was found. The capsule named Integrity carried 4 people to the edge of what any human had reached and brought them home. The name was chosen by the crew. It means wholeness, adherence to something larger than the moment, the willingness to do the hard thing honestly. That is what the mission was, and that is what the road ahead requires. We are going back. The only question is how carefully we walk the path that Artemis II opened.